The Big Bang did not bang. There was no explosion, no sound, no flash of light tearing through primordial darkness. This cosmic birth, the moment we've been taught marked the beginning of everything, happened in complete and utter silence. The universe didn't announce its arrival. It simply began. And in that silent genesis lies our first clue about its ultimate fate. Close your eyes. Picture nothing. Not darkness, not emptiness. Actual nothingness. An absence so complete, your mind recoils from it. Now, watch as this nothingness transforms. Not with a thunderous roar, but with a whisper. Space itself stretches into existence, pulling time along with it. No observer witnesses this birth. No coordinates mark this place. There is no outside from which to view it. The universe doesn't expand into anything. It simply becomes. You've been told a story about our cosmic origins that's both true and fundamentally misleading. The universe as we know it did emerge approximately 13.8 billion years ago, but everything you visualized about that moment is likely wrong. Our language fails us here. We speak of before the Big Bang, but time itself began in that moment. We imagine the universe expanding outward, but there is no exterior space into which it grows. The very frameworks we use to comprehend reality break down at this threshold. What if everything ends not with destruction, but with profound silence? What if the final fate of all existence mirrors its beginning? Not with collapse, but with expansion so vast that all meaning dissolves into the void. The question of whether the universe can live forever isn't merely about time. It's about the nature of existence itself. Look up at the night sky. Those stars you see, they're already ghosts. The light reaching your eyes has traveled for years, decades, even millions of centuries. You're not seeing what is, you're seeing what was. Now imagine this. The most distant galaxies are accelerating away from us at this very moment, faster and faster, approaching the speed of light. Eventually, they'll cross a cosmic horizon from which their light can never reach us again. They won't cease to exist, but for all practical purposes, they'll vanish from our observable universe forever. This cosmic acceleration, this mysterious dark energy pushing everything apart, wasn't part of our understanding until 1998. For nearly a century, physicists debated whether the universe would eventually collapse back into itself in a big crunch or expand forever at an ever-slowing rate. Neither scenario proved correct. Instead, we discovered something far more unsettling. The expansion is speeding up. The universe isn't just growing, it's running away from itself. You might wonder how emptiness itself can expand. Isn't empty space just nothing? But space isn't nothing. It's something. It bends, it warps, it ripples like the surface of a pond. And right now, it's stretching apart faster than you can comprehend. Between galaxy clusters, new space is being created every second. The cosmos isn't expanding into existing emptiness. It's manufacturing new emptiness, pushing everything further apart. And this process appears to be accelerating without limit. If you could witness the universe 1 trillion years from now, you wouldn't recognize it. The Milky Way and its closest neighbors will have merged into one enormous island galaxy, floating in what appears to be an otherwise empty cosmos. All other galaxies will have receded beyond our cosmic horizon, their light unable to outrace the expanding void between us. The night sky will grow darker, star by star, galaxy by galaxy, until only our local group remains visible. Future astronomers, if any exist, will look up and see nothing but darkness beyond their home galaxy. The evidence of a vaster universe will have vanished entirely. They might conclude they are alone in an otherwise empty cosmos. The fate of our universe hinges on a substance we cannot see, cannot touch, and barely understand. Dark energy, the name itself reveals our ignorance, pervades every cubic centimeter of space. It doesn't dilute as the universe expands. It doesn't gather into clumps like matter. It remains constant, pushing outward with steady pressure, accelerating the cosmic expansion with each passing eon. But what is it? We don't know. The greatest minds on Earth have proposed dozens of theories: a property of the vacuum itself, a new field, a modification of Einstein's gravity. But we remain in the dark about the dark. Hold your hand out in front of you. In the space occupied by your palm, quantum fluctuations are constantly occurring. Particles and antiparticles briefly flashing into existence before annihilating each other. This quantum effervescence, this subtle fizzing of reality, may be the source of dark energy. The vacuum itself might not be empty, but filled with a seething, invisible energy that drives the universe's accelerating expansion. If this theory is correct, the universe won't just expand forever. It will expand faster and faster until atoms themselves are torn apart. What if our universe is just one bubble in a cosmic foam? What if there are others, countless others, expanding, contracting, popping into existence and collapsing back into nothingness? Multiverse theory suggests that our universe, with its peculiar physical laws and constants, is but one possibility among an infinite landscape of potential realities. Some may collapse quickly, never giving rise to stars or planets. Others might expand forever, but remain sterile, devoid of the complex chemistry necessary for life. We may exist in a rare bubble where conditions allow for consciousness to arise, and ask these very questions. The heat death awaits us, a final state of maximum entropy where no usable energy remains, where all stars have burned out, all black holes have evaporated, and the temperature approaches absolute zero throughout an inconceivably vast cosmos. But is this truly the end? Or could new universes bud from quantum fluctuations in the vacuum, creating fresh islands of order in an otherwise dead sea of entropy? Perhaps universal death is merely part of a greater cycle, a cosmic breathing where expansion leads not to permanent stillness, but to the conditions necessary for rebirth. You exist in a universe already experiencing middle age. The era of star formation is slowing. The heyday of galaxy building has passed. The cosmos has transformed most of its hydrogen into heavier elements, leaving less fuel for new stellar birth. We live in the autumn of creation, when the great processes that created the conditions for our existence are gradually winding down. And yet, autumn has its own splendor. The universe today, rich with complex elements, stable planetary systems, and the intricate chemistry of life, couldn't have existed in the chaotic youth of creation. If you could somehow stand outside time and watch the entire cosmic story unfold, would you see an ending? Or would you witness something more profound, a transformation rather than a conclusion? The question of whether the universe lives forever may ultimately depend on how we define life. If life means maintaining the current cosmic order, stars burning, galaxies evolving, new planets forming, then no, the universe as we know it cannot live forever. But if life means change, transformation, and the persistence of physical law, then perhaps the cosmos never truly dies, but merely transforms into states beyond our current comprehension. The most profound paradox may be this: we exist to ask these questions because the universe will eventually die. The arrow of time, the irreversible flow from past to future, from order to disorder, creates the conditions necessary for memory, consciousness, and thought. Without entropy, without the gradual dissolution of order, complex structures like your brain couldn't process information or form new memories. We comprehend the universe's mortality only because we ourselves are mortal, products of the very forces that will ultimately unravel the cosmic tapestry. When you gaze at the night sky, you're looking not just at space, but at time itself. Those distant galaxies exist in states of reality that have already transformed beyond what you observe. The universe you see doesn't exist anymore. It has already changed, already moved one step closer to its ultimate fate. And in this revelation lies both terror and wonder. We can never truly know the cosmos as it is, only as it was. We are forever looking backward, even as we strain to glimpse the future. Most of us carry a comfortable image of our universe, a vast but ultimately comprehensible cosmic ocean, stars drifting like islands in an inky sea, galaxies swirling like celestial pinwheels. This mental picture serves us well enough for daily life. But reality, as it often does, refuses to conform to our simplifications. The truth of our cosmos is stranger, more beautiful, and infinitely more unsettling than these gentle metaphors suggest. Let's begin with something you think you understand: space itself. You move through it every day, navigating its three dimensions with unconscious ease. Forward and backward, up and down, left and right. Simple. Except space isn't simply a container holding reality. It's an active participant in cosmic events, a dynamic fabric that stretches, contracts, and warps in response to mass and energy. When Einstein revealed that gravity isn't a force but a curvature of spacetime, he wasn't speaking metaphorically. The sun doesn't pull Earth into orbit. It creates a depression in the fabric of reality that our planet rolls around like a marble on a stretched rubber sheet. This isn't poetry. It's literal description. And this malleable stage on which our cosmic drama unfolds wasn't always here. Rewind the cosmic film far enough, and space itself becomes compressed beyond comprehension. The early universe wasn't just hot. It was a furnace where time itself was still learning to move forward, where the four fundamental forces we know today existed as a single, unified superforce. Physics, as we understand it, breaks down in this primordial epoch. Our equations shatter against the wall of the Planck era, that first inconceivable fraction of a second, when the universe was smaller than an atom but contained all the potential of everything that would ever exist. You've been told that nothing can travel faster than light, Einstein's cosmic speed limit. Yet the infant universe expanded faster than light speed during a period called inflation. How is this possible? Because it wasn't matter moving through space, it was space itself expanding, multiplying its dimensions exponentially in less than a billionth of a trillionth of a second. This isn't a violation of relativity. It's the universe exploiting a loophole in its own laws. The horizon of our observable universe, everything we can potentially see, was once compressed into a volume smaller than an elementary particle. Regions of space now separated by billions of light-years were, in that moment, quantum entangled. Neighbors. If the universe has no edge, then where does it begin? Where does it end? The question itself contains a flawed assumption. You imagine the universe as an enormous but finite bubble expanding into something else, some exterior void. But there is no exterior. The universe isn't expanding into anything. It's simply becoming larger. Think of the surface of a balloon being inflated. An ant walking on the balloon's surface can travel in any direction without finding an edge, yet the surface is finite. As the balloon expands, the distance between any 2 points on its surface increases, but there's no center of expansion on the surface itself. Our three-dimensional space may work the same way, curving through higher dimensions we cannot directly perceive. We speak confidently about 13.8 billion years of cosmic history, but this certainty rests on assumptions that grow increasingly tenuous as we probe deeper into time and space. The cosmic microwave background, that faint afterglow of the Big Bang, provides our earliest direct window into the past, showing us the universe as it appeared when it was merely 380,000 years old. Before that, our knowledge becomes increasingly theoretical, built on mathematical models and indirect evidence, and at the very beginning, physics as we know it simply fails us. Quantum mechanics and general relativity, our two most successful physical theories, cannot be reconciled in the extreme conditions of the nascent universe. Like two languages with no common translator, they speak of the same reality in fundamentally incompatible terms. You've heard of black holes, regions where gravity becomes so intense that not even light can escape. But have you truly contemplated what happens at their centers? There, matter compresses into a singularity, a point of infinite density where space-time itself collapses. Our equations break down completely. This isn't merely a failure of measurement or observation. It's a fundamental breakdown in our understanding of reality. Singularities represent cosmic blind spots, places where the rulebook of physics is not just bent, but shattered. And the Big Bang itself may have emerged from just such a singularity, a point where time and space, as we understand them, ceased to have meaning. The universe we observe appears finely tuned for existence. Change the strength of gravity by a fraction of a percent, alter the mass of fundamental particles by tiny amounts, modify any of dozens of physical constants by seemingly insignificant degrees, and stars wouldn't shine, planets couldn't form, chemistry would falter, and life as we know it would be impossible. This cosmic coincidence, this apparent fine-tuning, demands explanation. Some see evidence of design, others invoke the anthropic principle. We observe these particular constants, precisely because they allow observers to exist. Still others propose the multiverse, an infinite landscape of universes with different physical laws, of which ours is simply the one where complexity and consciousness could evolve. In your everyday experience, cause precedes effect. The past influences the future, never the reverse. But in the quantum realm, time's arrow becomes blurred. Particles can become entangled across vast distances, responding to each other's states instantaneously in ways that seem to ignore the light speed limit of causality. The delayed choice quantum eraser experiment suggests that observations made in the present can retroactively determine what happened in the past. These quantum phenomena don't fit neatly into our macroscopic understanding of time as a one-way street. They hint at a reality where past, present, and future may be less distinct than we imagine, where time itself might be an emergent property rather than a fundamental dimension. The observable universe contains approximately 2 trillion galaxies, each housing hundreds of billions of stars. The cosmic inventory includes roughly 10^80 atoms, a number so vast it defies comprehension. Yet visible matter, everything we can see with our most powerful telescopes, represents less than 5% of the universe's total mass-energy content. The rest? Dark matter and dark energy. Names that mask our ignorance. We call them dark, not because they're simply unilluminated, but because they're invisible to our instruments, detectable only through their gravitational effects, or, in the case of dark energy, through the accelerating expansion of space. We're, like sailors, mapping an ocean by observing the movements of our ship, never seeing the water itself. Dark matter forms an invisible scaffold throughout the cosmos, its gravitational influence holding galaxies together and guiding the formation of cosmic structure. Without it, galaxies would tear themselves apart, spinning too quickly for their visible mass to hold them together. Yet, despite decades of searching, we've never directly detected a dark matter particle. We've built ever more sensitive detectors deep underground, shielded from cosmic radiation. We've looked for subtle signals in the afterglow of the Big Bang. We've searched for evidence in cosmic ray interactions. The particles, if they are particles at all, continue to elude us. And then there's dark energy, the most abundant yet mysterious component of our universe. Unlike matter, which dilutes as space expands, dark energy appears constant throughout space, its density unchanging. As the universe grows larger, dark energy becomes increasingly dominant. Its pressure, negative pressure, counterintuitively, drives cosmic acceleration, pushing galaxies apart at an ever-increasing rate. But what is it? A property of the vacuum itself? A new field permeating space? A modification of Einstein's theory of gravity? Each explanation comes with its own theoretical challenges. None fully satisfies. If dark energy maintains its current properties, the universe will not only expand forever, it will expand faster and faster. Galaxies outside our local group will accelerate beyond our cosmic horizon, their light unable to reach us. Stars will burn out. Black holes will evaporate through Hawking radiation. Protons themselves may decay. In the far, far future, trillions upon trillions of years hence, the universe will approach a state of maximum entropy. No usable energy will remain. No work can be done. No new structures can form. This heat-death scenario represents a cosmos, not destroyed but exhausted, a universe that doesn't end but simply fades into eternal, unchanging darkness. But there's a profound contradiction lurking in our understanding of cosmic fate. On one hand, the second law of thermodynamics tells us the universe inexorably moves toward increasing disorder, toward that final state of heat death. On the other hand, the universe we observe has been growing more complex, more structured, more organized over billions of years. From primordial hydrogen to stars, planets, and the intricate biochemistry of life, cosmic evolution seems to defy entropy's dictates. How can a universe destined for maximal disorder give rise to such extraordinary complexity along the way? This paradox suggests we're missing something fundamental about the relationship between entropy, information, and the arrow of time. As we peer deeper into space, we look further back in time. The most distant galaxies we observe appear to us as they were billions of years ago when the universe was young. This means our understanding of cosmic history is actually a composite view, assembled from observations of different epochs. We don't see the universe as it is, we see it as it was, across a vast range of different times. And this raises a profound question. If the light from distant regions hasn't had time to reach us yet, how can we be confident about our picture of the cosmos as a whole? What might exist beyond our cosmic horizon, forever invisible to us? How much of reality remains perpetually outside our view? Our cosmic story has reached its most profound chapter, where the mathematics grows abstract, but the implications become deeply personal. We stand at the edge of known science, peering into the abyss of what might be possible. The question of our universe's immortality isn't merely academic, it's existential. To answer it, we must confront the most radical theories modern physics has to offer. Imagine reality as a film reel, where time is not flowing, but every moment already exists. In Einstein's universe, this isn't just poetic imagery. It's a mathematical reality. General relativity describes a block universe, where past, present, and future coexist simultaneously, each moment as real as the last or next. The flow of time, that sensation of perpetual movement from then to now to later, may be nothing more than a psychological construct, a trick of consciousness, rather than a fundamental aspect of reality. From this perspective, the universe doesn't evolve or change, it simply is, complete and eternal, encompassing all events that ever were or will be. Yet quantum mechanics tells a different story. At the subatomic scale, reality appears fundamentally probabilistic, with particles existing in superpositions of possible states until observed or measured. The future isn't written. It's a branching tree of possibilities collapsing into actuality moment by moment. These two perspectives, Einstein's deterministic block universe and quantum mechanics' probabilistic reality, represent one of the greatest unresolved contradictions in modern physics. And in this contradiction may lie the key to understanding whether our universe has an ultimate fate or exists in a state of perpetual becoming. Consider the black hole, a cosmic object so extreme it punctures the fabric of space-time itself. As matter collapses under overwhelming gravity, it reaches a point where density becomes infinite and volume becomes zero, a singularity. Here, our mathematical descriptions break down completely. It's not that we lack precise measurements or more powerful telescopes. It's that our conceptual frameworks themselves fail. And yet, black holes exist. We've imaged them. We've detected their gravitational waves. We've mapped their effects on surrounding matter and light. Nature seems untroubled by our inability to describe what happens at their centers. The Big Bang may represent a similar singularity, a point where the entire observable universe was compressed into an infinitesimal volume of infinite density and temperature. But singularities make physicists deeply uncomfortable. They signal a breakdown in our theories, places where the mathematical models that so accurately describe the rest of reality suddenly produce nonsensical infinities. Nature abhors such infinities, suggesting our theories are incomplete rather than reality being pathological. What lies beyond these cosmic blind spots? Loop quantum gravity, one of several competing theories aiming to reconcile quantum mechanics with general relativity, suggests singularities may not exist at all. Instead, when matter reaches extreme density, quantum effects may create a repulsive force that prevents complete collapse. In this scenario, black holes don't contain singularities, but incredibly dense cores where space becomes granular, composed of indivisible units, rather than the perfectly smooth continuum Einstein described. And if this applies to black holes, it might apply to the Big Bang as well. Not a beginning from nothing, but a transition from a previous state, perhaps even a previous universe. Imagine our universe as a bubble, one of countless billions floating in a vast, higher-dimensional sea. In string theory's brane cosmology, our three-dimensional reality exists on a membrane, or brane, floating within a higher-dimensional bulk space. Other branes may exist parallel to ours, perhaps occasionally colliding. Such a collision could release enormous energy that, from our perspective confined to the brane, would appear as a sudden expansion from a point. The Big Bang, in this view, wasn't the absolute beginning, but a violent interaction between our brane and another. This cyclic model suggests our universe may be one phase in an eternal cosmic dance, expanding and contracting in perpetual rhythm, never truly beginning or ending. You've likely heard of the multiverse, the idea that our universe is just one of many, perhaps an infinite number, each with different physical laws and constants. But the concept comes in several distinct flavors, each with profound implications for cosmic immortality. The inflationary multiverse suggests that during cosmic inflation, that period of exponential expansion in the universe's first fraction of a second, quantum fluctuations could have created bubble universes with different properties. Our observable cosmos would be just one bubble in an ever-expanding sea of universes, constantly spawning new regions that inflate into full universes of their own. The many worlds interpretation of quantum mechanics offers an even more radical vision, a decay multiverse, where every possible outcome of every quantum interaction actually occurs, creating new branches of reality that diverge from our own. In this view, the universe as a whole never dies because it encompasses every possible timeline, every possible future. While individual branches may experience heat death or other endings, the totality of existence continues to branch and evolve eternally. Your consciousness may be confined to one branch, but reality itself experiences all possibilities simultaneously. Consider time itself, that mysterious dimension we move through without choice or control. Newton saw time as absolute, flowing uniformly throughout the cosmos. Einstein revealed it to be relative, flowing differently depending on gravity and velocity. But what if time is neither absolute nor relative, but emergent, not a fundamental dimension, but a secondary phenomenon arising from more basic quantum processes? Theoretical physicist Carlo Rovelli's thermal time hypothesis suggests that time's arrow, its apparent one-way flow, emerges from thermodynamics and quantum entanglement. Time, in this view, isn't a river carrying us forward, but a pattern of correlations between quantum events. This perspective opens a startling possibility. Time might not be universal or fundamental at all. Different regions of the cosmos, different collections of entangled particles, might experience different times flowing at different rates, or even in different directions. And if time isn't fundamental but emergent, asking whether the universe exists forever may be like asking whether a circle has an end point. The question itself may be based on a misconception of reality's fundamental nature. Cosmologist Roger Penrose proposed the conformal cyclic cosmology, a model where the universe undergoes endless cycles of expansion, but with a twist. Each cycle begins with a Big Bang and ends with the evaporation of the last black hole, leaving nothing but massless particles traveling at light speed. From the perspective of these particles, time and distance become meaningless due to the effects of special relativity. The universe reaches a state mathematically identical to the hot, dense conditions of the Big Bang. Infinity loops back on itself, and a new cycle begins, not after the old one, but as a continuation of the same reality under different conditions. In this model, our universe is immortal, not because it persists unchangingly, but because it transforms endlessly, each end becoming a new beginning. Vacuum decay represents one of the most unsettling potential fates for our cosmos. Quantum field theory suggests that our universe might not be in its lowest energy state. It could be in a false vacuum, temporarily stable but fundamentally precarious. A quantum fluctuation in even a single point in space could trigger a bubble of true vacuum that would expand at the speed of light, rewiring the laws of physics as it grows. Inside this bubble, the fundamental forces, particle masses, and physical constants would take different values, likely incompatible with matter as we know it. This wouldn't be mere destruction, it would be a complete rewriting of reality's rulebook. What makes this scenario particularly chilling is that it could be happening already, somewhere beyond our cosmic horizon, a wavefront of transformed physics racing toward us at light speed. offering no warning before it arrives. The idea of a cyclic universe has appeared in many forms throughout history. In the ekpyrotic scenario, based on string theory, our three-dimensional universe periodically collides with another brane in higher dimensional space. Each collision produces a Big Bang, creating the conditions for a new cosmic cycle. This model doesn't require inflation to explain the universe's uniformity and flatness, instead attributing these features to processes occurring before the collision. If true, our universe has neither beginning nor end, but exists in an eternal cycle of collision, expansion, cooling, and eventual recollision. Emergent gravity, proposed by theoretical physicist Eric Verlinde, suggests that gravity isn't a fundamental force, but an emergent phenomenon arising from the thermodynamics of quantum information. Just as temperature emerges from the collective behavior of countless atoms, rather than being a property of individual particles, gravity might emerge from the collective behavior of quantum bits of information. If correct, this would require us to completely reimagine the basic forces structuring our universe. Furthermore, it might offer new perspectives on dark energy and cosmic acceleration. Perhaps these aren't caused by an actual substance or field, but by information-theoretic processes playing out across cosmic scales. Imagine the entire universe as a quantum computer, a system processing information according to the laws of quantum mechanics. Theoretical computer scientist Seth Lloyd has proposed that the cosmos itself can be modeled as a quantum computational device, with each interaction between particles representing an elementary computation. From this perspective, the universe's evolution isn't just a sequence of physical events, but a vast calculation unfolding across space and time. This computational universe model raises profound questions. What problem is the universe computing? Is the calculation finite or infinite? Could a universe that processes information eternally be considered immortal, even if its physical structure eventually decays? The holographic principle, inspired by black hole thermodynamics, suggests that all the information contained in a volume of space can be represented by information encoded on the boundary of that region. Just as a hologram on a credit card is a two-dimensional surface that creates the illusion of three dimensions, our apparently three-dimensional reality might be encoded on a distant two-dimensional surface. This isn't merely metaphorical, it's a mathematical correspondence being actively explored by physicists, especially in the context of string theory. If our universe is indeed holographic, questions about its ultimate fate may need to be reformulated in terms of the evolution of this boundary information, rather than the apparent physical cosmos we experience. The deeper we probe into cosmic immortality, the more we encounter paradoxes that stretch the limits of human comprehension. These aren't merely puzzles awaiting solution, but fundamental tensions in our understanding of reality itself. They represent the frontiers of knowledge, where certainty dissolves and possibility expands. Consider Olbers's paradox, first formulated in the 19th century but still haunting cosmologists today. In an infinite, eternal universe filled with stars, every line of sight should eventually end on a star's surface. The night sky should blaze with the light of countless distant suns, as bright as the surface of our own star. Yet the night is dark. This simple observation, the darkness of the night sky, tells us something profound. Either the universe is not infinite in size, not eternal in age, or is expanding in such a way that distant starlight is redshifted beyond visibility. The darkness between stars represents cosmic history written in absence rather than presence. The cosmic horizon problem presents another paradox. Regions of space on opposite sides of our observable universe have never been in causal contact. Light from one has never had time to reach the other, even over the entire 13.8 billion-year history of the cosmos. Yet, these regions show nearly identical temperatures and densities. How could areas that never communicated have such similar properties? Cosmic inflation offers one solution. These regions were in contact before inflation exponentially expanded. Space, but this merely pushes the question back. What caused inflation? Was it a one-time event unique to our universe's birth, or a recurring process creating new bubble universes eternally? The flatness problem compounds the mystery. Observations indicate that the universe's spatial geometry is remarkably close. To flat, parallel lines remain parallel. The interior angles of triangles sum to exactly 180 degrees. This flatness requires the universe's expansion rate and matter density to be perfectly balanced to 1 part in 10 to 60, an inconceivable level of precision. It's like balancing a pencil on its point so perfectly that it remains standing for billions of years. This extraordinary fine-tuning demands explanation. Is it mere coincidence, evidence of design, the result of cosmic inflation, or a selection effect, where only universes with such properties can develop observers to notice them? At quantum scales, reality becomes even more paradoxical. The double-slit experiment reveals that particles like electrons behave as waves when not observed, creating interference patterns, but behave as particles when measured. This observer effect, where the act of measurement appears to collapse quantum possibilities into definite realities, has prompted endless debate. Does consciousness itself play a role in determining physical reality? Does the universe exist in a superposition of all possible states until observed? Or do all possibilities manifest in parallel universes? As the many worlds interpretation suggests, quantum entanglement, what Einstein called spooky action at a distance, allows particles to maintain instantaneous correlations regardless of the space separating them. Measure one entangled particle, and its partner instantly reflects that measurement, even if it's on the opposite side of the universe. This seems to violate the light speed limit of information transfer, yet experiments consistently confirm it occurs. Bell's theorem and subsequent experiments have ruled out hidden variable explanations, forcing us to accept that reality at the quantum level is fundamentally non-local. Either information travels faster than light, violating relativity, or separate parts of the universe aren't as separate as they appear. The information paradox in black hole physics presents another profound contradiction. Quantum mechanics insists that information cannot be destroyed, only transformed. Yet black holes appear to destroy information. Anything falling into them loses its distinct identity, reduced to just 3 properties: mass, charge, and angular momentum. When black holes eventually evaporate through Hawking radiation, where does this information go? Physicists have proposed various solutions: information encoded on the event horizon, preserved in subtle correlations in the radiation, or transferred to parallel universes. But no consensus exists. This paradox cuts to the heart of whether information, like energy, is conserved eternally or can truly be lost. Time itself presents paradoxes that challenge our understanding of cosmic mortality. If time began with the Big Bang, what came before? The question itself may be meaningless, as before implies temporal sequence, and time itself may have no meaning outside our universe. Yet humans instinctively resist the notion of an absolute beginning. We seek causes for effects, antecedents for consequences. The concept of a first moment, uncaused and unprecedented, creates profound cognitive dissonance. Various theories attempt to address this: eternal inflation, cyclic models, quantum fluctuations from nothing, but all eventually confront the same barrier. Our minds evolved to understand phenomena within time, not the origin of time itself. The arrow of time points inexorably from past to future in our experience, yet the fundamental laws of physics work equally well in either temporal direction. Drop a glass, and it shatters, a clear demonstration of increasing entropy. Yet nothing in the basic equations governing the atoms in that glass prevents the reverse process. They're perfectly reversible. The asymmetry we experience, memories of the past but not the future, eggs breaking but never unbreaking, stems from initial conditions rather than physical law. The universe began in an extraordinarily low entropy state, and its evolution toward higher entropy gives us time's arrow. But why did the universe begin in such an improbable low entropy configuration? And if entropy eventually reaches its maximum, does time itself cease to have meaning? Recent astronomical observations have revealed another cosmic puzzle. The universe's expansion is accelerating, driven by dark energy. Yet the measured value of this dark energy density is approximately 10 to 120 times smaller than quantum field. Theory predicts it should be. This discrepancy, the cosmological constant problem, represents the largest gap between theoretical prediction and observation in the history of science. If the theoretical value were correct, the universe would have expanded so rapidly that galaxies could never have formed. Some theorists invoke the anthropic principle. We observe this unlikely value precisely because it allows for our existence. But this explanation leaves many unsatisfied. Does the answer lie in supersymmetry, extra dimensions, or modifications to quantum theory itself? The resolution would profoundly impact our understanding of whether the universe can exist eternally. The universe appears remarkably suited for complexity and, eventually, life. Change the strength of the strong nuclear force by a few %, and stars couldn't forge the heavy elements essential for chemistry and biology. Adjust the electron mass, and molecules couldn't form. Alter the cosmological constant slightly, and galaxies wouldn't exist. This apparent fine-tuning has three main explanations: incredible coincidence, highly improbable; intelligent design, philosophically complex; or the multiverse, physically extravagant. In a multiverse where all possible physical parameters exist somewhere, we inevitably find ourselves in one of the rare universes compatible with our existence. But this explanation comes at a cost. It suggests our universe isn't special or unique, but merely one habitable island in a vast cosmic archipelago, most of which would be sterile and lifeless. Eternal inflation theory suggests that once cosmic inflation begins, it never entirely stops. While some regions, like our observable universe, exit the inflationary phase and begin normal expansion, other regions continue inflating exponentially, spawning new bubble universes eternally. This creates a fractal multiverse structure where inflation produces new universes faster than any process could possibly destroy them. In this scenario, the multiverse as a whole achieves immortality, even if individual universes eventually die through endless reproduction. Yet this theory creates its own paradoxes. If inflation produces infinite universes with all possible configurations, how can we assign meaningful probabilities to cosmic outcomes? The measure problem in eternal inflation remains unsolved despite decades of work by leading theorists. The cyclic nature of scientific understanding itself represents a philosophical paradox. Throughout history, each generation has believed it approached the final truth about reality, only for subsequent discoveries to reveal previously unimagined complexities. Newtonian mechanics gave way to relativity, which now seeks reconciliation with quantum mechanics. Each theory didn't prove the previous one entirely wrong, but showed it to be a special case of something larger, applicable only within certain boundaries. This pattern suggests humility about our current understanding. The theories we've discussed, inflation, dark energy, strings, brains, loops, may themselves be approximations of deeper structures we haven't yet imagined. The ultimate fate of the universe may involve processes currently beyond our conceptual horizon. Recent developments in dark energy research have revealed yet another cosmic tension. Measurements of the universe's expansion rate using different methods, the cosmic microwave background versus direct observation of supernovae, give slightly but significantly different results. This Hubble tension suggests either systematic errors in our measurements or something fundamentally missing from our cosmological models. Perhaps dark energy isn't constant, but evolves over time. Perhaps new particles or forces influence cosmic expansion in ways we haven't detected. This discrepancy reminds us that even our most basic understanding of cosmic evolution remains tentative, subject to revision as new evidence emerges. The very concept of nothing presents a profound paradox relevant to cosmic origins and fate. When physicists speak of nothing, they typically mean a vacuum state. Technically not nothing, but a seething quantum foam where particles and antiparticles continuously flicker in and out of existence. True nothingness, the complete absence of space, time, fields, laws, and potentiality, may be logically impossible. As philosopher Martin Heidegger put it, why is there something rather than nothing? This question confronts not just the origin of our universe, but the possibility of absolute non-existence. Can something truly become nothing? Or does existence in some form, even if radically transformed beyond our current physics, persist eternally by logical necessity? We've been discussing the universe as if we were outside it, detached observers contemplating distant galaxies and abstract theories. But we are not separate from this cosmic drama. We are within it, of it, created from its substance. Every atom in your body was forged in the heart of a dying star. The iron in your blood, the calcium in your bones, the carbon that forms the basis of your DNA, all were synthesized in stellar furnaces billions of years ago and scattered across space when those stars exploded. You are, quite literally, made of stardust. And this isn't poetic license, it's chemical fact. What does it mean to be ephemeral beings in a potentially eternal cosmos? If the universe expands forever, accelerating endlessly into the darkness, what becomes of consciousness, of memory, of meaning itself? The carbon atoms currently arranged as your brain may persist for trillions of years, eventually scattered across light years of space. But the particular arrangement that creates your thoughts, your memories, your sense of self, that will dissolve in mere decades. You are a momentary pattern in the cosmic flow, a brief eddy in the river of time. If time is an illusion, as Einstein's physics suggests, then everything you've ever done, every choice you've ever made, every moment of joy or sorrow you've ever experienced might have already happened infinite times before, and might happen infinite times again. Your life may not be a sequence unfolding, but a complete object existing all at once in a higher dimensional reality. Your sense of moving through time, of having a past and facing an uncertain future, may be a psychological construction rather than a fundamental truth. What becomes of free will, of moral responsibility, of the meaning of choice in such a universe? Look at your hands. Really look at them. The particles that form your flesh have existed since the beginning of time. They were present at the Big Bang. They may endure until the heat death of the universe, until the final evaporation of the last black hole. They were something else before they were you, and they will be something else after. You are not a permanent entity, but a temporary configuration. A brief moment when certain particles of the cosmos arrange themselves into a pattern complex enough to contemplate its own existence. There is a profound terror in this realization, but also a kind of cosmic communion. What if the universe is alive, and we are just its fleeting thoughts? Panpsychism, the philosophical position that consciousness is a fundamental property of matter, present in some form at all levels of reality, has experienced a revival among certain scientists and philosophers. If consciousness isn't something that emerged only in complex brains, but a basic aspect of reality itself, then perhaps the cosmos as a whole possesses a form of awareness vastly different from, but fundamentally, related to our own. Perhaps our individual consciousnesses are to universal awareness what individual neurons are to the human brain. Components of something larger, something integrated, something whole. Now, take a breath and attempt to grasp the scale of your own insignificance. The observable universe spans approximately 93 billion light-years. If the entire cosmic history were compressed into a single Earth year, human civilization would occupy only the final minutes of December 31st. If the Earth were shrunk to the size of a grain of sand, our galaxy would span an area larger than North America. And our galaxy is one among 2 trillion. Your entire life, everything you will ever experience, everyone you will ever love, every thought you will ever think, occupies an infinitesimal fraction of cosmic space and time. This is not merely humbling, it is horrifying. The human mind did not evolve to comprehend such vastness. Our neural architecture developed to track social relationships in groups of 150 individuals, to navigate territories measuring dozens of square miles, to plan for seasonal changes and modest futures. The cosmic scale breaks our intuitive understanding of reality. We cannot truly visualize a billion of anything, let alone billions of light-years or billions of galaxies. We resort to analogies, to scaled-down models, to mathematical notations, but the true immensity remains fundamentally incomprehensible. And yet, paradoxically, you matter. In a universe of unimaginable vastness, consciousness may be vanishingly rare. The particular arrangement of matter that allows you to contemplate your own existence, to wonder about the cosmos, to feel awe and terror and love, this arrangement may be among the rarest phenomena in existence. If the universe is a near-infinite ocean of mindless particles, then consciousness may be the rarest element of all, more precious than gold, more fleeting than subatomic particles that decay in microseconds. What if we are the universe's attempt to understand itself? What if consciousness isn't incidental to cosmic evolution, but central to it? Perhaps the universe achieved immortality not through its physical structure, but through the emergence of minds capable of contemplating eternal questions. Perhaps we, and any other conscious beings that might exist throughout the cosmos, are the universe's way of perceiving its own existence, of recording its own history, of contemplating its own destiny. Consider a more disturbing possibility. What if our universe is a simulation, a complex computation run on unimaginably advanced technology by beings in a higher reality? The simulation hypothesis, seriously discussed by philosophers and physicists, suggests that if any civilization ever develops the capability to run detailed simulations of conscious beings, they would likely run many such simulations. Statistically, this would mean that simulated minds vastly outnumber real ones. If so, the odds overwhelmingly favor us being among the simulated rather than the simulators. And if our universe is a simulation, questions about its ultimate fate become questions about the intentions of its creators. Will they let the program run forever? Will they terminate it when it no longer interests them? Are we living in an auditory immortal reality or one with a predetermined end date? If dark energy continues to accelerate cosmic expansion, a time will come, roughly 100 trillion years from now, when all galaxies beyond our local group will have receded beyond our cosmic horizon. Their light will never reach us again. Future civilizations, should any exist, will look up at a nearly empty sky and might reasonably conclude they are alone in the universe. The evidence of the vast cosmos we observe today will have vanished irretrievably. Our knowledge, our awareness of the billions of galaxies currently visible, may be a cosmic accident, possible only during this brief era when light from distant regions can still reach us. We may be living in a uniquely privileged moment of cosmic history, the only time when the true scale of the universe is observable. Does this privilege carry responsibility? Are we cosmically obligated to preserve this knowledge, to ensure it outlives our ephemeral species? In infinite time, given the finite number of ways particles can arrange themselves, every possible configuration must eventually repeat. In an eternal universe with eternal atoms, your exact atomic arrangement, down to the last subatomic particle, would eventually reassemble itself. This is the concept of eternal return, contemplated by philosophers from Nietzsche to Kaufmann. Given infinite time, you would exist again, exactly as you are now, reading these exact words, having these exact thoughts. Not metaphorically, not symbolically, but literally, atom for atom, thought for thought. And not just once, but infinitely many times across the endless expanse of eternity. If the universe is truly immortal, then nothing that happens within it happens only once. Everything recurs eternally. How would you live differently if you knew every moment of your life would repeat endlessly throughout cosmic time? All these grand cosmic theories, these mathematical models, these philosophical speculations, they pursue a singular, haunting question. Can the universe as we know it persist eternally? We've explored expanding space and accelerating galaxies, quantum, fluctuations and thermodynamic heat death, multiverses and emergent time. But perhaps we've been asking the wrong question all along. Perhaps the most profound truth lies in a more disturbing possibility, one that inverts our entire perspective on cosmic immortality. What if the universe is already dead, and we are just experiencing its last echoes? Consider information, not as an abstract concept, but as the fundamental currency of reality itself. In quantum mechanics, information is physical. It cannot be created or destroyed, only transformed. Every particle interaction, every gravitational influence, every electromagnetic wave carries information about the state of the universe. And information requires a medium, something to encode it, to preserve it, to transmit it. Now imagine the universe not as expanding outward from a hot, dense beginning, but as collapsing inward toward an ultimate end, a final singularity where all information, all history, all reality compresses into an infinitesimal point. This Big Crunch would mirror the Big Bang, creating a perfect temporal symmetry. But here's the mind-bending twist. What if we're not living in the expanding phase, but in the contracting phase? What if what we perceive as cosmic expansion is actually contraction viewed from the inside out? Information flowing backward through. Time would appear to us. Creatures evolved to perceive time flowing from low entropy to high, as an expanding, cooling universe rather than a contracting, warming one. Our perception of the arrow of time, our entire causal framework, would be reversed from the underlying reality. We wouldn't be witnessing the birth and life of a cosmos, but experiencing its final moments played backward. A cosmic film running in reverse. Watch as galaxies swirl in cosmic darkness, their spiral arms rotating with ponderous grace across billions of years. These galactic titans, each containing hundreds of billions of stars, appear to be flying apart from each other, carried by the expanding fabric of space. But what if this apparent motion outward is actually a gathering inward, viewed through the distorting lens of reversed temporal perception? What if the darkness between galaxies isn't expanding emptiness, but collapsing fullness? Space itself, condensing toward an ultimate recompression? The cosmic microwave background, that faint afterglow of the Big Bang, bathes the universe in radiation from all directions, a perfect black-body spectrum at precisely 270 Kelvin. We interpret this as the cooled remnant of primordial fire, but it could equally represent a final state approaching from what we perceive as the future, the universe's information encoded at the lowest possible temperature before. The reversal of time, the rewinding of thermal processes, begins. Dark energy, that mysterious force accelerating cosmic expansion, takes on a new significance in this inverted view. Rather than driving galaxies apart forever, it becomes the mechanism by which the universe gathers itself for its final compression. What we perceive as an ever-quickening expansion might actually be an ever-quickening contraction experienced in reverse. The universe isn't living forever. It's already ended, and we exist in the temporal echo of its collapse. Visualize the cosmic horizon, that ultimate boundary beyond which we cannot see. Light from regions beyond this horizon hasn't had time to reach us in the 13.8 billion years since the Big Bang. We imagine these distant realms existing now, simultaneously with us. Their light still en route to our telescopes. But in a universe where time flows backward from a final singularity, these regions don't represent unobserved spaces. They represent unmanifested potentials, parts of reality that haven't yet collapsed into the final singularity from which our experienced timeline emerges. This perspective doesn't mean the universe lacks immortality. It transforms our understanding of what immortality might mean. The cosmos may not endure eternally into the future, but might contain all possible futures already, encoded in what we perceive as its past. The universe's immortality wouldn't be about endless duration, but about perfect information preservation. Every event, every thought, every quantum fluctuation preserved forever in the ultimate cosmic compression. Imagine standing at the event horizon of a supermassive black hole. Before you stretches a gravity well so deep that light itself cannot escape. Matter spirals inward in a luminous accretion disk, heated to millions of degrees by friction and gravitational stress. From your perspective, objects falling toward Multiverse. The black hole appear to slow down as they approach the horizon, their light becoming increasingly redshifted, time itself seeming to dilate nearly to stoppage. But, from the falling object's perspective, nothing unusual happens at the horizon. It crosses smoothly into the black hole's interior. The universe itself may be similar, experienced differently depending on one's temporal perspective. From inside the flow of time as we experience it, the universe appears to be expanding toward heat death. But viewed from outside time altogether, the cosmos might be a perfect four-dimensional structure, a complete object containing all events that ever were or will be, with no true beginning or end. The most profound scientific theories often don't simplify our understanding, but complexify it in meaningful ways. They don't answer all questions, but transform the questions themselves. And so it may be with cosmic immortality. The universe may be neither mortal nor immortal in conventional terms, but might exist in a state of temporal transcendence that renders the distinction meaningless. Not endless duration, but timefulness beyond time. Watch as stars explode in ibit, magnificent supernovae, blasting their elemental contents across interstellar space in expanding shells of luminous gas. These cosmic cataclysms appear to us as endings, stellar deaths, yet they seed the galaxy with the elements necessary for new stars, new planets, new life. What we perceive as destruction is simultaneously creation. Perhaps the universe operates. Similarly, at the largest scales, its apparent end simultaneously its beginning, its death simultaneously its birth. As you contemplate these possibilities, consider the strangest implication of all. Consciousness itself may be integral to this cosmic process. The universe requires observers to translate quantum possibilities into actualities, to collapse wave functions into definite states. What if conscious observation isn't merely witnessing reality, but participating in its creation? What if the universe achieves immortality not through endless physical duration, but through the preservation of information in conscious experience? Through you? Look again at the night sky. Those distant galaxies, those ancient stars, those unfathomable cosmic voids, they exist in your consciousness as patterns of neural activity, as electrochemical signals, as subjective experience. The universe you perceive isn't just out there. It's in here, in the intricate architecture of your mind. And if consciousness is a fundamental rather than incidental feature of reality, then perhaps the cosmos achieves a kind of immortality through the very act of being perceived, being understood, being contemplated. Now consider this final, vertiginous possibility. If time is indeed circular, if information is perfectly preserved in the cosmic cycle, if consciousness plays a fundamental role in manifesting reality, then perhaps the universe never truly dies because it never truly lives. It simply is, complete and eternal, encompassing all times, all possibilities, all perspectives simultaneously. And somewhere within that perfect totality, you exist, not just now, not just once, but always, an essential thread in the cosmic tapestry, never to be added, never to be removed, eternally woven into the fabric of everything. If the universe is infinite in any meaningful sense, temporally, spatially, informationally, then somewhere out there, in some form or manifestation, another version of you is contemplating these very same cosmic mysteries. Perhaps they've reached different conclusions. Perhaps they've glimpsed truths that elude you. Perhaps they are you, separated not by space or time, but merely by perspective, by the angle from which you view the perfect, complete, and eternal cosmic totality. We've journeyed across space and time, through mathematical abstractions and philosophical quandaries, seeking an answer to what might be the ultimate question. Can the universe, this vast, mysterious stage upon which our brief lives play out, continue forever? The quest has led us not to certainty, but to ever-deepening mystery, to paradoxes that challenge our very conception of reality. Perhaps this is as it should be. Perhaps the cosmos, in its fundamental nature, transcends our evolved capacity for understanding, not merely beyond our current knowledge, but beyond the very architecture of minds shaped to navigate the macroscopic world of moderate scales and speeds. Yet, we persist in asking. We build more powerful telescopes, more sensitive detectors, more sophisticated mathematical models. We peer into the quantum foam and the cosmic void with equal curiosity. This striving itself this reaching beyond our limitations, may be the most profound aspect of consciousness. We know we cannot grasp infinity, yet we try. We know we cannot visualize 11-dimensional space, yet we construct equations describing it. We know we cannot directly experience the birth or death of a universe, yet we piece together the evidence, constructing narratives that stretch our minds to the breaking point and beyond. The universe we observe, this expanding, cooling, evolving cosmos, bears the imprint of a fiery genesis some 13.8 billion years ago. The primordial hydrogen and helium forged in that ancient crucible still makes up the majority of ordinary matter. The cosmic microwave background still bathes us in radiation from that distant event. The galaxies still rush away from each other, carried by the expansion of space itself. These observations are not in question, but their interpretation, the story we construct around them, remains open, subject to revision as our understanding deepens. Will the universe expand forever, accelerating endlessly into eternal night? Will quantum fluctuations eventually trigger a phase transition, rewriting the laws of physics in a bubble of true vacuum that expands at the speed of light? Will dark energy strengthen over time, eventually tearing apart atoms themselves in a big rip? Will the cosmos reach maximum entropy, a state of perfect equilibrium where no further change is possible? Or will some as yet undiscovered principle intervene, altering the cosmic trajectory in ways we cannot currently imagine? Science provides multiple possible answers, each supported by mathematical consistency, but awaiting definitive observational evidence. Perhaps there is no single correct answer. Perhaps the question itself contains flawed assumptions about the nature of time, of existence, of continuity. Perhaps asking whether the universe is immortal is like asking whether a circle has a beginning, a question arising from the limitations of our conceptual framework, rather than a meaningful inquiry about reality itself. Consider your place in this cosmic drama. You exist now, in this particular moment of cosmic history, when stars still shine, when galaxies still form, when life still evolves. You belong to a species that has developed the capacity to contemplate its own origins and the fate of the universe that spawned it. This capacity is not separate from the cosmos. It is the universe becoming aware of itself, matter organized into such precise complexity that it can model its own existence, project its own future, reconstruct its own past. In you, the universe questions itself. Your atoms were forged in cosmic furnaces and catastrophic stellar deaths. Your molecular structures self-organized according to principles embedded in the laws of physics. Your consciousness emerged from electrochemical processes shaped by billions of years of evolution. You are not merely in the universe, you are of it, a natural expression of its properties and potentials. And in your brief moment of existence, you participate in the universe's own self-discovery. What does it mean to contemplate cosmic immortality from within the very system whose fate we question? It's like a character in a novel, wondering if the story continues beyond the final page. The question itself may be meaningful only from perspectives we cannot adopt, from outside time, from outside physical existence, from outside the constraints of beginning and ending that structure our experience. Yet, the question haunts us. It matters to us whether reality itself has an expiration date. It matters whether the cosmic story has an ending or continues eternally in forms we might not recognize. It matters whether the entire grand edifice of existence, from quarks to consciousness, from dark matter to desire, from bosons to bewilderment, represents a temporary deviation from nothingness or an eternal process of becoming. Watch as a Supernova erupts in distant space, its light reaching us after traveling millions of years, its brilliance briefly outshining its entire host galaxy. In that cataclysmic stellar death, new elements are created, new possibilities emerge. In cosmic destruction lives cosmic creation. Perhaps the universe operates similarly, at the grandest scale. Its apparent mortality, the necessary condition for its eternal renewal. Now contemplate the night sky once more, this time with fresh perspective. Those stars, those galaxies, those vast cosmic voids, they're not just out there, separate from you. They're aspects of a single cosmic process in which you participate. The boundaries between observer and observed, between subject and object, between consciousness and cosmos, may be as illusory as our separation of space from time before Einstein revealed their unity. What if the immortality of the universe isn't about endless duration but about the transcendence of time itself? What if the cosmos exists not in time, but with time? Time being a dimension of its structure rather than an external framework within which it evolves. The universe wouldn't need to last forever because, in a profound sense, it would encompass all time already, complete and perfect. This perspective doesn't answer our initial question. It transforms it. Instead of asking whether the universe will exist forever, we might ask whether forever itself is a meaningful concept at the cosmic scale. Instead of wondering whether reality will eventually cease, we might consider whether cessation itself is merely a phenomenon within reality rather than applicable to reality as a whole. The study of the cosmos continually reminds us that our intuitions, shaped by evolution to navigate the middle world of moderate sizes, speeds, and time frames, often fail us when contemplating the very large, the very small, the very fast, the very energetic. Our common-sense notions of before and after, of here and there, of something and nothing, repeatedly dissolve when subjected to the acid test of cosmological inquiry. And yet, paradoxically, the very minds that find themselves bewildered by cosmic mysteries are themselves products of cosmic processes. The brains that struggle to comprehend quantum superposition and inflationary multiverse theory are organized according to principles embedded in the laws of physics. There is a profound circularity here. The universe has organized a portion of itself into conscious beings capable of investigating its own nature, yet perpetually limited by the constraints of the very organization that enables their inquiry. This circularity need not be vicious. It might instead represent a kind of cosmic bootstrapping, reality becoming progressively more aware of itself through the evolution of increasingly sophisticated conscious subsystems. Your contemplation of universal immortality might not be separate from the universe's own self-investigation. Your questioning might be the cosmos questioning itself, using the temporary configuration of matter called you as its instrument of inquiry. If so, then perhaps the immortality of the universe encompasses not just the persistence of matter and energy, but the preservation of meaning, the mathematical relationships, the informational patterns, the structures of experience that constitute reality at its most fundamental level. Perhaps nothing that has meaning truly vanishes, even if its physical manifestation transforms beyond recognition. What haunts us most about cosmic mortality isn't the thought that matter might rearrange itself, that entropy might maximize, that the lights might go out. What haunts us is the thought that it might all have been for nothing, that the extraordinary emergence of mind from matter, of meaning from mechanism, might ultimately signify nothing, leaving no trace, serving no purpose beyond its momentary existence. But what if meaning doesn't require permanence? What if significance doesn't depend on eternity? What if the value of existence, of consciousness, of understanding, of connection, lies precisely in its transience, rather than despite it. Perhaps cosmic immortality isn't necessary for cosmic meaningfulness. Perhaps the universe doesn't need to live forever to matter infinitely. And yet, the possibility remains, tantalizing, vertiginous, awe-inspiring, that the cosmos might indeed persist eternally, not necessarily in its current form, but in some state that preserves the essence of what exists now. The laws of physics, the mathematical structures underlying reality, the informational patterns that constitute the universe's history, these might transcend any particular physical manifestation, continuing in forms we cannot currently imagine. The most honest answer to our initial question, can the universe live forever, might be a profound and resonant, perhaps, not from lack of investigation or intellectual courage, but from recognition of the limits of our current understanding and the vastness of what remains unknown. This, perhaps, isn't a temporary placeholder awaiting a definitive answer. It might be the most accurate reflection of reality's fundamental nature, neither definitively mortal nor definitively immortal, but existing in a state that transcends this dichotomy entirely. As you continue your own journey through the cosmos, your brief but extraordinary moment of consciousness within the vast sweep of cosmic history, carry this question with you. Let it inform your perspective on the world around you. Let it remind you of the profound mystery at the heart of existence. Let it connect you to the grand cosmic process of which you are a part. Look up at the night sky. Consider that the light reaching your eyes has traveled across unimaginable distances and through vast spans of time to reach you in this moment. Consider that your ability to contemplate the source of that light, to wonder about its journey, to ask about the ultimate fate of the stars that emitted it, this capacity for questioning is itself one of the most extraordinary phenomena in the known universe. The questions we've explored have no final answers, at least not yet, perhaps not ever within the framework of human understanding. But the questioning itself connects us to something beyond our individual lives, beyond our species, beyond our planet. It connects us to the cosmos itself, to the universe not as an external object, but as the totality of which we are a part. In the span of a human lifetime, we cannot know whether the universe will persist eternally, but we can know this. For a brief moment in cosmic history, the universe organized a portion of itself into beings capable of contemplating eternal questions. In your awareness, in your questioning, in your sense of wonder, the universe achieves something remarkable, something perhaps as significant as immortality itself. It achieves self-awareness, self-questioning, self-wonder. The universe may have no end, or it may transform beyond anything we can recognize as existence. But in this moment, here and now, it lives in your consciousness, in your questioning, in your search for meaning. And perhaps that's the most profound form of immortality possible. Not endless duration, but infinite significance in the moment. Not perpetual existence, but eternal relevance in the now. The universe may or may not live forever, but through your wondering, it lives completely.